Hello. In this video, we're going to look at some applications of the Arclength formula, S equals theta R, where theta is in radians. And I'm calling this part 2 because in an earlier video, first I looked at how did this formula arise, like why does it make sense? And then in another video, I looked at one set of applications where basically an object or a person follows a curved path. So we're looking at a distance that is curved. And then the second application that we're going to look at in this video is when you use arc length to approximate the length of a chord in a circle, and two conditions must be met. The circle must be large and the central angle is small, less than 10 degrees. So let me kind of look at that first to see about these criteria. Right. So they're saying here the circle must be large and the central angle must be small. So first, let's take a look at what is a chord. So when I look at a circle, right, a chord is basically a distance between any 2 points. Like I could say between this point and that point. That's a chord. Or I could have said between this point and this point. That's a chord, right? Any line that joins any 2 points on a circle. Now, we are looking at things, we need to work with central angles. So the chord that we would be looking at then would be something like you start at a central angle. So you start at the center of the circle and you have a central angle. Now if you look at the chord there, and my central angle is very large, obviously much larger than 10 degrees. The chord here, this distance is much smaller, right? Or much shorter than this distance. So here we have the arc length, S, right? And here we have the chord. So you can see that this curved distance is a lot larger or longer than this chord because the central angle is very, very large. But if instead I were to make the central angle quite small, right? Then what you see if I were to expand this is that you'd have like you'd have a chord like that, and because you're coming around here like this little curve, you're only taking a little piece of it. It's almost the same length as the chord. It's a little bit longer because it's curved, but it's almost the same length. So as long as you have a small central angle, right, not a big central angle, and of course you also need a large circle. Okay. You also need a large circle. Let's think about if you had like a really small circle, it's turning on itself so quickly that it's hard to get a chord to be the same length as the arc length. They're very close to it. So you really need a very, 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 very large circle so that it's so spread out that it's almost linear. It isn't, but it's curving so slowly. It's not curving so quickly. It's curving so slowly that it's almost like a line, just a teeny bit longer, okay? So that's what we have to make sure that we meet these conditions. Circle must be large, central angle must be small. 10 degrees or less is probably a good ballpark to use. So let's take a look at let's look at an application of that then. All right, so let's say here, suppose a natural gas tank 4 kilometers away subtends an angle of 3.21 degrees. We want to approximate the height of that tank to the nearest meter. Okay, get this straight here. Okay, so let's say then you're here, and we'll just take it from the ground. Sorry, this is meant to be a straight line here due east, and we look at this tank, right? And it subtends. This central angle is 3.21 degrees, so much less than 10, so it's small. And remember, it's 4 kilometers away, so it's on a circle that's huge. But the circle, here's the center of the circle, and this, which is 4 kilometers, right, is the radius. So it's going in each direction, right? If we kept going, it'd be like huge, right? This would be a very, 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 very large circle, okay? Where here now, this little curved portion is almost the same as that, the height of the tank. So now the height of the tank is actually a straight line. The arc length is a curve. So the arc length is a teeny bit longer and is approximating the chord. All right. So now we are going to say, let's go ahead and work with the arc length formula. and we're going to say, put a new fresh paper over that. These bleed so much, these Sharpies. So S equals theta R. Remember, theta has to be in radians. So they gave me theta and they gave me R. All I have to do is convert theta into radians. So 3.21 degrees. I want to go from degrees into radians. Okay. So I don't write it, but it's understood, pi radians. So pi is just a number, right? And then so here's theta. All of this is theta. And now the radius is 4 kilometers. And all I have to do is multiply all these. When I multiply all these out, I'm going to get the S is 0.244 kilometers. And they want us to round to the nearest meter, so I have to move the decimal over 3 places. So 10, 100,000, so I'd have 244 meters. Okay, so that's what I'd have. And remember, what's happening is if I were to expand it, the tank is something has a vertical height, and the arc length is coming along here like this. Sorry, something like that. And that's this teeny little curved portion. So what I'm then supposed to tell you is that the arc length approximates, that means approximates, the chord, which is the length or the height of the gas tank. Okay, and which was 244 meters. All right, so that's our first example. Now let's take a look at a second example. So they talk about spy satellites, and they have cameras that can distinguish objects that subtend angles of as little as 5 times 10 to the negative 7 radians. Okay, if such a satellite passes over a particular country, let's see, at an altitude of 155 meters, I'm sorry, not meters, miles, how small of an object can the camera distinguish? Give your answer in meters to 1 decimal place, and also in inches to 1 decimal place. I guess so that we'll be familiar with it and understand what it what it is. All right, so I think the hardest or most challenging thing of this is to see the picture, to understand what's the radius, what's the angle, because the application of S equals theta R is just plug it in. But essentially, remember, you're here at the point of view of the observer. Let's see if I can get the other one too. So here also, you were the observer here. And so then you went out the radius and created your circle, right? So here, from the point of view of the observer, the distance between the observer and that object is the radius, right? So the radius is 155 miles. And so here, you go out this way and you're making your circle, right? So you're... And you have to make the sound effects, by the way. Oh, sorry, it actually be maybe a little smaller here. But anyway, still a really big circle. And essentially, there's a little object down here. If I could, there's an object that has a certain length, and you're basically using the arc length of this circle that's a little bit curved to approximate the length of that object. And we want to know how small can the object be. All right, so now we know that we basically have what that object subtends, right, from way over here where this is 155 miles, and this theta is 5 times 10 to the negative 7 radians. Right? So that's really, really small, right? Because that's 1, 2, 3, 4, 5, 6, 5, right? 1, 2, 3, 4, 5, 6, 7. 5 times 10 to the negative 7 radians. So that's very small, way less than 10 degrees, I think. Well, I don't know, I have to, but I'm pretty sure. All right, so here S equals theta R. Theta is already in radians, so you'd say S equals 5 times 10 to the negative 7, right? Times then 155 miles, right? And then will be in miles. They want the answer first in meters and then in inches. So you'll just kind of basically go, I'm going to go ahead and go to the inches just to go all the way down so you can see it. But basically you'd have what? In 1 mile, they're telling us there's 1,609 meters. So you'd be done right there for the meters. And then I'm just going to keep going and go to the inches. They tell us to use 39.3 Oh no, sorry, 1 meter. Sorry. Let me change that. We're in meters in the numerator, so I want meters in the denominator. So 1 meter is 39.37 inches. So when I'm done, the miles cancel out, meters cancel out, and I'm going to be in inches, right? So when you do all this, you're going to have 4.91 inches, which is about 5 inches, right? That's incredible, isn't it? I mean, like, that means that these satellites can see very small objects, and this is really, really old information, so I can't even imagine now what they might see. They probably see their pupil or something like that. The last thing I want to do is just show you this 10 to the negative 7. So if we do here, let's see if I can do this. 10, oops, can you say that? Raised here, so the caret. And then I'm going to use parentheses because I've got to put 2 things there, negative 7, right? The negative and the 7. And now press enter, I'll get that. So then I go times 5. Let's go ahead and do this. Times 155 times 1609 times 39.37. There's that 4.9, right? 4.91. Okay, and that's it. Thanks so much for listening.